Hello, my name is Uri Katel. I will show you what we have done in the VC Lab at the Technion as a part of the C-Bridge project in a matter of semantic enrichment of bridge models. During the presentation, I will try to answer several questions. What is the enrichment of a model? Why do we need it? What are the inputs and the output of the process? How do we do it? What we succeed to do, and where our results still limited. As you can see in the slide, visually the model after the 3D recognition looks very good. Each of you can easily see the columns of the bridge, but for the computer it's not more than an extruded mass. The computer doesn't know that this mass is a column and can't refer to it. If we want to get the surface area of the columns in the model, we have to calculate it manually. Here comes the enrichment process, where we add in meaningful information to an existing model. And if we look for a more precise definition of semantic enrichment, it can be defined this way. Semantic enrichment of building models refers to an automatic or semi-automatic addition of meaningful information to a digital model of a building or a structure by software that can be deduced new information by processing rules or applying machine learning. So as the input we have the model of plane geometry and additional information queried from the BMS. The enrichment process can be divided into 5 parts. We identify all the objects in the model, we aggregate them into groups, we number the objects, we create axes, and we reconstruct objects occluded in the laser scan. Our output is an IFC model with all additional information. The input have to be readable by our system, so it have to comply some rules. There are several ways to represent geometry in computers. The first one is combination of simple geometrical objects such as ball, conus, or box. Swept section also can be a way of representation of 3D objects. Another common way is surface representation of 3D objects. As you can understand, the information needed in each representation is different. For example, to check if two objects parallel, we can check the extrusion direction of the swept solid. In other representations, we can use one of the axes of the bounding box of the object. But how do we choose which of the axes to use? Another issue is that if an object will be created out of many small objects, our system will fail to recognize it. Overlapping objects is not something existing in real life, so it has to be eliminated from the model due to the need of proper representation. The slab seen partly from below and fully from above, and its division to separate objects can influence its recognition. Because we decided to use the IFC format, we have different ways to represent similar information. It's important to work out our way not only for our pipeline of information, but also to make our model usable by others. I want to show you an example of information we can add. Here we can see an example of an input with a plane geometry. IFC viewer shows us a capping beam above the columns marked in green. If we will look to the object properties, this object has no name and no bed ID. For all of us it's obvious that this picture we're looking to a capping beam, but the computer does not know it and cannot refer this particular object as to a capping beam. Another input that we can have is an Excel file with information from bridge management system. This is an example of how it looks. We used input from the Israeli BMS via Excel file. the additional information we save in conceptual object IFC building. Then we can refer to it inside CBIN as bridge object. Here you see the same bridge after our process, and you see that I have a new bed ID where we save the type of the object. In the moment we logically recognize the object during the process, we can change any of its properties. We decide to change the tag of the object in addition to the object type due to viewer limitation of not showing the object type. Then, how CBIN adding the information? Let's start with a simple example of a model with 3 objects and a rule set of 3 rules, where the first rule addresses only one object and the other rules compares pair of objects. Each of those rules will run in a loop on all available objects. For the first rule, it will be objects 1, 2, and 3. The other rules will run on all possible combination of object pairs. You can see that pair of object 2 and 1 is a different pair from pair of object 1 and 2. If a rule changing anything, it raises a flag of a change has been made. After all rules run on all objects, we checked if the flag is on. In that case, we turn off the flag and start all the rules from the beginning. In theory, we can make such a mistake in the rule set that 2 rules consequently change 1 bit of information back and forward, creating an infinite loop. We added another stop condition where the system will stop after a given amount of time. In the case of no changes has been made, the enrichment process will finish. This is how our interface look like. I will follow the numbers and quickly explain what we can do in each section. The first one, here you can see in what user you logged in. We think it's logical to give a separate user for each type of bridge because the difference in rules needed for the process. It's also the place where you can log out from the system. The second is the rules section. You can see below the list of the rules. By clicking on the rule, you can read and change it. The third, you can see a checkbox near each rule. This needed when you want to choose more than one rule. 4. Pressing this button, you can create a new rule. 5. This button will delete all checked rules. 6. Part of the rules create and reads user-defined variables that needed to follow the logic of the enrichment process. Pressing this button, you can see the list of already used new variables. Here is the rules set section, number 7. We group number of rules that have to work together into rule sets. Number 8. By checking one of those checkboxes, all the rules in the rule sets will be checked. Pressing this button number 9, you can create a new rule set. Number 10. Pressing this button, you delete all the checked rule sets, not the rules itself. Number 11. In this file section, you have list of all files appearing in the server for the particular user, of course. Number 12. Unlike the rules, and the rule set, you don't have checkbox, cause you can act only on one file at a time. Number 13. Pressing this button, you download from the server to your local computer the chosen file. Number 14. Pressing this button, you delete from the server the chosen file. Number 15. Pressing this button, you run all the checked rules on the chosen file. A new file will be created. In the list, this will be the enriched file. An example of a process in real time. We have several types of rules. Rules with two acting objects. That kind of rules compares between features of two objects. Rules that checks feature of one object. Rules uses only the initial information, and some rules can use additional information that has been found during the process. We came up with an algorithm that checks if the rules that we have enough for identifying all the objects. Moreover, it arranges rule sets for identifying each couple of objects. However, if one of the objects were occluded in such a way that it disappeared from the 3D recognition, like it happened with the bearings in the Haifa bridge, its counterpart can be not identified too. We solve this by creating additional rule sets where each object in a pair with another object too. Our algorithm of compiling the rules checks the logic of the rules and eliminates the logical false positive. However, false positive, due to model mistakes, theoretically can appear. Here you can see the model viewed in Solibri FC model viewer before and after edification of the capping beam that you saw before, and the rule recognizing it in C-beam as it looks in our interface. We group the objects into systems. Some assignments are unique. For example, the object cannot be a part of the superstructure and the substructure in one time. Others are not unique. For example, safety barrier can be a part of the superstructure and the safety system both at once. There are groups assigned by function, like safety, drainage, etc. There are other groups that are more conceptual, like aggregating all the deck slab particles into one group. Here you can see a simple rule that adds the capping beam we have seen before into the substructure, and the way we can see it in the model viewer. We want to create access for the bridge. We have to choose the objects to help us to define them, such as main girders for longitudinal access and abutment and capping beam for lateral ones. The axes will be aligned with the objects and lie on their projection to XY plane. In addition, we have an algorithm that extends the axes, number them, and make them to follow the longitudinal curvature of the bridge if it appears. Here we can see a simple rule that creating a lateral axis where our cap and beam appears and number it as C. We need to number the object so it will be easy to understand what object we are referring to. The main issue we have to deal with is that all the rules run all the time, and we don't know the order that C-beam will meet the objects. In addition to that, we don't want to create and maintain lists external to the system with global variables to sort the objects. We came out with an algorithm based on idea of bubble sort to number the objects within C-beam. This is an example as a simple representation of how numbering algorithm works. In the beginning, the algorithm gives 1 to each column as a number. When it picks up 2 columns, it checks if they are the same axis and if they have the same number. If the answer for both of the questions is positive, we increase the number of the column with the higher ordinate. The number is compiled out of 2 parts, the axis number and the number inside the axis. If we need to number objects that are not lying on an axis, like a transverse beam, we do the same algorithm in 2 directions. Here we can see the rule as you see it in C-beam and the result in the model viewer. The algorithm is self-implemented in the backstage and transparent for the user. Parts of the bridge can be occluded in the laser scan as a reason of difficulties in placing the scanner. That happened in the scan of the Haifa bridge. We invented an algorithm that lengthening the girders to its logical lengths and saving both of the geometries, the original one and the newly created. We also added a placeholders in places bearings have to be found but missed in our model due to the height of the laser scanner. Here you can see the missing lengths of the girders, the rule as you can see it in C-beam. Again, the algorithm is transparent for the user, and the model after enrichment with the newly created geometry. This is flowchart of lengthening algorithm. We start with calculating the minimal distance from the edge of the girder to the center axis of the adjacent capping beam. We do it in the background with the help of a global variable. Then, the algorithm picks up one girder and one capping beam at a time. We check if they are closed. We do not want to extend girder over the next span. We check if the distance is more than the global variable and if it have enough overlap to have support underneath. If the girder have to be lengthened, we check either it from the start or from its end. If from the end, we just copy it to the same position, making remark of recreated geometry and giving it a new length. If we have lengthened from the start, we have to calculate the new starting point and copy the beam to the new starting point with the recreated geometry remark and giving it the proper length. In the beginning of the project, we decided how our result will look like. To meet that standard, our model passes through a post-processor that saves all the information we added in the correct way. As any project, we have several limitations. We have to have more resilient and redundant rules. We're still focusing only on main objects of the bridge but we can expand to other objects in the same way. We haven't dealt with unifying objects that came in parts from the geometry recognition. We dealt only with straight bridges with straight axes. Curved axes can be interesting issue. We have learned today why do we need the semantic enrichment, how do we do it, what exactly we can do, and how is good our result. Thank you for listening.